Welcome to part 2 of Agentic AI in Life Sciences. This technical deep dive focuses on building regulated, clinical-grade agentic systems. We will cover advanced prompting strategies, multi-step reasoning chains, and self-improving feedback loops using Python. This program is brought to you by the Series of Thoughts team as part of the AI Foundation series. In this module, you will master 4 key areas: role-based prompting for expert persona emulation, COT and React frameworks for step-by-step reasoning in action, prompt refinement and chaining for multi-step pipelines, and finally, feedback loops to implement self-correcting agents for clinical workflows. Chapter 1 focuses on implementing role-based prompting with Python. The goal is to guide AI to emulate expert personas like pathologists or genetic counselors, ensuring structured, safe, and professional outputs required in regulated environments. Role-based prompting instructs the AI to adopt the persona of a domain expert. This is critical in life sciences because clinical outputs require precise medical terminology, professional and auditable language, and the ability for the agent to recognize its expertise boundaries. An effective role-based prompt has 4 essential components. These include a persona definition specifying credentials, behavioral guardrails defining what the agent must avoid, an output schema enforcing structured formats, and an escalation protocol instructing when to defer to human experts. In Python, roles are defined as structured data and injected into the LLM system message for reproducibility. Key steps involve defining a clinical role data class, building a prompt template, passing the system message, and validating the response against the expected schema. Guardrails are a regulatory requirement for role safety. They include scope limitation, constraining the agent to its specialty, confidence thresholds, requiring the agent to express uncertainty, and an audit trail, logging all role assignments and responses for compliance. Chapter 2 introduces chain of thought, or COT, and React prompting. These conceptual frameworks enable guided reasoning and allow agents to plan, reason, and take actions in complex biomedical workflows. Chain of thought, or COT, instructs the model to show its reasoning step by step. In clinical contexts, COT is vital for auditability, making the reasoning inspectable, and for error detection, allowing flaws to be identified precisely where they occur. React extends CADA by interleaving reasoning with action steps. The agent thinks, plans an action like querying a database, observes the result, and then continues reasoning. This allows the agent to use external tools for validated final answers. The choice between COT and React depends on the task. COT is better for internal reasoning, such as differential diagnosis. React is needed when external tool access, like checking drug interactions or lab lookups, is required. Applying COT and React in Python requires defining a reasoning template and, for React, registering tool functions. We then build an agent loop to implement the thought, action, and observation cycle, ensuring the final output is validated and logged. In a biomedical use case, a React agent processing an adverse event first thinks about the interaction. It then acts by querying a drug database, observes the major interaction, reasons again, and finally provides a classified conclusion after looking up MedRay codes. Chapter 3 covers prompt instruction refinement. This involves systematically modifying the prompt components, like role, task, context, examples, and output format, to produce regulated, auditable, and machine-validated LLM outputs. Prompts need iterative refinement because first draft prompts often result in vague outputs, schema non-compliance, or a lack of necessary safety boundaries. In regulated environments, a prompt must be a controlled specification. Refinement uses 5 levers: role, adjusting the persona's specificity; task, sharpening the objective; context, providing relevant background; examples, adding few-shot learning; and output format, enforcing structured schemas for validation. Iterative refinement in Python follows a structured loop: generate, evaluate quality, identify the weakest link, and modify and retest. This cycle mirrors the Plan-Do-Check-Act quality management methodology, fitting naturally into life sciences AI development. A real-world scenario shows refinement in action, starting with a vague baseline prompt, adding a role and format in iteration 2, and finally adding context and examples in iteration 3 transforms the output into a fully compliant, audit-ready specification. Chapter 4 introduces chaining prompts for agentic reasoning. This involves building multi-step AI workflows by linking the output of one prompt to the input of the next. with non-negotiable validation at every junction in clinical systems. Prompt chaining decomposes a complex task into focused subtasks, such as extraction, classification, analysis, and reporting. Each step has a clear operation, and its validated output feeds into the next, mirroring established clinical workflows. Chaining beats single prompt approaches by reducing the risk of hallucination due to narrow scope, enabling inter-step validation to catch errors early, and offering modular debugging. Critically, it ensures regulatory traceability with discrete, loggable artifacts at every step. Validation is the critical link in every chain. Every junction must have a validation gate to verify the output programmatically before it becomes the next step's input. Checks include schema validation, completeness checks, and terminology verification against standard vocabularies. LangChain provides the orchestration primitives needed to build these robust prompt chains in Python. This includes architectural blueprints for complex pipelines, such as those used for pharmacovigilance signal reporting. Production chains require robust error handling to prevent silent failures. Strategies include retrying failed steps with backoff, using fallback prompts if validation fails, and routing the case to a human reviewer after exhausting automated retries. Chapter 5 explores LLM feedback loops. This involves building self-improving systems where agents use feedback from their own actions to iteratively refine outputs, forming the foundation of truly autonomous clinical AI. The feedback loop is an iterative refinement process. The agent generates an output, evaluates it against quality criteria, critiques the deficiencies, and then revises the output using the critique as additional context. This repeats until a quality threshold is met. Feedback loops are essential in life sciences to ensure outputs meet deterministic quality standards. They reduce the human review burden, maintain consistent quality at scale, and create an audit-friendly improvement trail for regulators. Implementing feedback loops in Python requires defining an evaluator function to score outputs, a critic prompt to identify specific issues, and composing a revision prompt that incorporates the critique. Termination conditions, like a maximum number of iterations, must be set. Monitoring performance metrics, such as first pass accuracy, average iterations needed, final pass rate, and the escalation rate, ensures that feedback loops are efficiently improving quality and are not stuck in unproductive cycles. The Capstone project focuses on an adaptive clinical trial feasibility agent. This task involves configuring a multi-agent system for drug safety monitoring, utilizing expert AI roles, tool assignment, and autonomous collaboration on a safety signal report. Your mission is to act as an AI engineer and configure a production-ready multi-agent pipeline. This involves defining expert roles, assigning tools like drug databases, enabling collaboration through chaining, and implementing self-correction via feedback loops. The multi-agent architecture will involve 3 specialized agents working in sequence: a pharmacovigilance specialist, a medical reviewer, and a regulatory writer. An orchestrator will manage the handoffs and critical validation gates between each agent. The Capstone project brings all concepts together. Role-based prompting defines each agent's persona. Cut and React enable reasoning and tool use. Prompt refinement maximizes quality. Chaining and feedback loops connect and self-correct the validated workflow. In summary, Part 2 highlights that precision comes from roles, structured reasoning from Cut and React, robust workflows from validated prompt chains, and consistent quality from self-improving feedback loops. These are the foundations of auditable clinical AI. You now have the complete toolkit for building clinical-grade agentic AI systems. Apply these patterns to your regulatory and clinical workflows. Start small, add validation, and then layer in feedback loops. Every iteration will make your system more reliable and impactful.